In this video, we consider the language L equals description of D such that D is a DFA and the language of D equals sigma star. And we are going to show that L is decidable. So we use the following facts in this proof. So the first fact is that EQ DFA is decidable. Okay, we know this by theorem 4.5. Okay, and we're going to let E be the decider for EQ DFA. Okay, so as a reminder, what is EQ DFA? EQ DFA is the language of strings, so that, let's call this not D, let's call it F. F1 and F2, such that language of F1 equals language of F2. Okay, so basically EQ DFA is the language of strings that represent a description of a DFA followed by the description of another DFA, and it's the case that the language of the two DFAs is the same. It means that all of the same strings are in the language. Okay, so that's our first fact. First fact. Okay, our second fact is that sigma star is regular, and so it's recognized by a DFA. Okay, and we can just remember it looks like this. Some DFA that recognizes sigma star will look like this. And this is going to be for all transitions A in sigma. Okay, so that DFA is going to recognize sigma stars. Alright, fact 3. A Turing machine can construct a DFA to recognize the language of sigma star given sigma as input. Okay, so TM can construct a DFA to recognize sigma star given sigma as input. Okay, so what do we mean? It means that if we that we can build a Turing machine that if we provided an alphabet, it can actually construct the machine that recognizes all strings over that alphabet. And just to convince ourselves that this is true, we can write the description of this machine, of the DFA, and it's simple. It's supposed to be brackets, sorry. Bracket. It's simple, and we could set up a Turing machine that would write this description. Okay. Okay, so this part, everything but delta, is independent of sigma. So here, if I'm given sigma as an input, I know I make a starting state called Q0, and that's all of the states I need. I have sigma as input. We're going to hold off on delta for a second. The start state is Q0, and then the only final state we have is also Q0. It's the only state in the machine. And then how would we define delta? We would define delta as delta of Q0 on, we'll say A, equals Q0 for all A in, sorry, I got ahead of myself, for all A element, this pen is really bad, sorry guys, of sigma. Yeah, I can't fix that. Okay. Alright. So we could algorithmically define this transition for each symbol in sigma, given that I have sigma as, okay, and then this would be a description of this machine I've created up here, and we can convince ourselves that a Turing machine could do this. Okay, and then fact 4 see if I can fit it down here, is that if a Turing machine is given the description of a DFA, it can retrieve the input alphabet sigma. So we're going to say a TM can get, I'm just going to say get sigma from a description of D. D is a DFA. Okay, so all of these facts together, let me just remind ourselves of the facts. So EQ DFA is double, and we're going to call its decider E. Sigma star is recognized by a DFA. A Turing machine can construct a DFA to recognize sigma star given sigma as input, and further, the TM can actually get sigma, this input that I need for this third fact, from a description of a DFA. Okay, so using these facts, we're going to define a Turing machine M that's going to decide L. Okay, so how do we construct M? Let's give its description on input D. And I'm going to just shorthand this, but D is the description of a DFA. We could have a step in here that says if D is not a valid encoding of a DFA, then reject. So that's it's implied here. I'm not writing it explicitly, but that's implied. Okay, so the first step would be locate and retrieve sigma from the description of D. Okay, and we said that's a fact, we can do this, so I can use that. Step 2, we're going to construct a DFA. We're going to call it S. Such that the language of S is sigma star. Okay, so here I'm just saying make this this DFA to recognize sigma star that's in this third fact that we said we could do. Okay, so we're calling it S. And then step 3, we're going to run E, the decider for EQ DFA, on the machines D and S. D was our input, S is the machine that recognizes sigma star, and accept if it does. Otherwise, okay, so if it doesn't accept, reject. Okay. So now we need to convince ourselves that this actually does decide L. So if M accepts, this means that E accepted DS, which means language of D is equal to the language of S, which was sigma star. Okay, and that's what we were asking. So M is going to accept if the language of D is sigma star. And just to remind ourselves, those are all the strings that should be in this language, right? It should be all the descriptions of DFAs where their language is sigma star. And we notice that if M rejects, it's because E rejects DS, which is because the language of D is not equal to the language of S, which was equal to sigma star. So language of S is sigma star. If language of D is not equal to the language of S, then language of D can't be sigma star, and then our machine will reject. And so those will be all the strings that are not in this language, which means that they are either, actually there's two cases because I said there's some implicit rejection here. Assuming that D is a DFA, then the language of D is not sigma star. There's the other case too, where D is not a DFA. But again, we said we're kind of handling this implicitly without writing it at the beginning of the machine. So it would have also rejected those strings as well. Okay? So that's one way to decide L. There's another way as well. We also know that EDFA is decidable. Okay, so this was by theorem 4.4. Okay, so what is EDFA? EDFA is the set of machine descriptions such that D is a DFA and the language of D is empty. Okay, so you can see a direct correlation here. EDFA is going to accept all the strings for which it's a description of a DFA, and that DFA's language is empty, it has no strings. And L is the set of machine descriptions where the DFA accepts all strings. Okay, so we have a complement relationship here. So let's see if we can use that. Okay, so let's let E prime be the decider for E DFA so I can reference it. Okay, so let's make another machine M prime, and its description is on input D, and again we're saying where D is a DFA. If it's not a DFA, immediately reject. Okay, so what are we going to do here? We are going to construct another machine. We're going to call it D prime. It's a DFA such that the language of D prime... Oh, is this what I mean to do? This is not what I mean to do. Hold on. I jumped ahead. Okay. We're going to construct D prime such that the language of D prime is the complement of the language of D. Okay, so how can we do that? We had an algorithm for the proof of closure of complement for regular languages that will do this. So basically, if I'm given a machine description, if I have a DFA, I want to accept everything that it rejects and reject everything that it accepts, and that will give me the complement. So how do I do that? If I take all of my final states and I make them non-final states, and then I take all of the previously non-final states and make them final states, now every time I entered into a final state in the original DFA, and therefore I would have accepted that string, I'm now going to enter a non-final state and I'm going to reject that string. Likewise, every time I ended up, after reading all my input, I ended up in a non-final state. Now after reading my input, that state has just become a final state, so I'm going to accept that string. Okay, so we can convince ourselves that we can do this. And just like we kind of walked through for the first proof, how a Turing machine could do this, you can imagine that as a Turing machine, you're looking at a description of a DFA, and it's in a recognized format. So you're going to be able to see the set of states Q, and you're also going to be able to see the set of final states F. Okay, and by marking, so we could, let's say, mark all of the final states in Q, and then in our new DFA description that we're writing on the tape, anything that's marked, we don't add that to our new set of final states. We only add the ones that are not marked. Okay, so we could do this algorithmically in finite time. Okay, so we have the language of the complement now, and as our second step we're going to run, that's supposed to be an E, not a sigma, run E prime on D prime and accept if it does. Otherwise, reject. Okay, so to convince ourselves that this actually works, we're going to notice a couple things. Note that the complement of sigma star is the empty set, and the complement of the empty set is sigma star. Okay, so see if I can stay on the same page. So if M prime accepts, this means E prime accepts, and I'm going to jump from the machine descriptions just to the language. No, I'm not. It's not technically correct. All right, we'll do the machine descriptions. Okay, so it meant that E prime accepted the description of D prime, which implied that the language of D prime is empty, which implies that the language of D prime complement is sigma star. And because the language of D, and then since the language of D prime complement is equal to the language of D, then this is equal to sigma star. Okay, so the machine accepts if the language of D was sigma star, which is exactly what we wanted it to do. And when does it reject? So M prime rejects when E prime rejects description of D prime, which is when the language of D prime is not equal to empty, which happens when the language of D prime complement is not all strings. Okay, so this also means that the language of D prime complement, which is equal to the language of D, is not sigma star. Okay, so now we have two different proofs showing that L is decidable.